Hello and welcome back to the CCENT journey with me, Ryan. In this next section, we're going to carry on with the routing element of the ICND1 blueprint, and particularly we're going to discuss the encapsulation, decapsulation and the packet rewrite section. Now this is something that we have discussed throughout the videos here and there, primarily at the OSI discussion, but I think it does warrant a video on its own to ensure that we're all on the same page, because this is one of the most important aspects of the CCENT. For those who don't know, you can contact me here on YouTube, on LinkedIn or Twitter. Before we get started, I just want to have a discussion regarding a topology I've put together. We have two hosts, PC1 and we have PC2. They're connected through a couple of switches and a couple of routers. And what we need to be able to do at the ICND1 level in order to achieve our CCENT certification is understanding the encapsulation and decapsulation process as the traffic flows from PC1 to PC2. And the most important part of that being what happens with the layer 2 and layer 3 PDUs, protocol data units, as it flows on a per hop through a switch or through a router. So again, this is something we talked about in the Open System Interconnect model, the OSI, where we had a discussion around the different layers, and I briefly talked about how the layer 2 header gets rebuilt on a per hop basis, but I didn't really give you a detailed understanding of why. So first of all, what we're going to do is give everyone a IP address. And what I've done is I've assigned a IP address to the PC, which is 192.168.0.100, and to PC2, which is 172.31.0.10. And you can see that each network, broadcast domain, however you want to call it, maybe network segment, has got its individual IP address. So in this broadcast domain here, they're using the 172.31.0.0/24, and my PC is using .10 in that range, and its default gateway to router 3 is using .1. Because we know that routers break up the broadcast domains, each link in a router will be in a different network. So here, this is one network, and I've conserved the IPs by giving it a /30, which is 4 IBs to usable. So this is the 10.0.1.1, 10.0.1.2. And then each hop has its own IP range. So again, the 10.0.0.0/30 is this network, with .1 being router 1, .2 being router 2, 192.168.0.0/24, and that's this network or broadcast domain. So again, it's understanding the terminologies that people use. Most of the people in the industry calls it a network. They say, how do I get to that network? Why can't I route through this network? Some people refer to it as broadcast domains, as subnets, but as long as you understand the theory and what they're trying to portray, and you understand the connotations around that, you'll be fine. What we also need for communication to work is our layer 2 physical addresses. So these are our MAC addresses. They're sometimes called physical addresses. They're called MAC addresses. They're sometimes called hardware addresses. And some people call them the burned in address, BIA. But ultimately, every NIC card, network interface card, on any device has a unique MAC. The first half of the MAC address, which is 3 bytes, is the organizational unique identifier, which identifies which vendor is that NIC card actually built by, and then the second portion of the MAC address is unique to that vendor. In turn, by doing that, we ensure that no vendor has the same MAC addresses as any other vendor. So this means that you can see PC1 and PC2 both have the MAC address. Here, they're written out in the format that the actual Windows places them in. And it doesn't really matter what format it is, as long as you can identify it being a MAC address. And we know MAC addresses are 48 bits with hexadecimal, meaning it can be anything from 0 to 9 and A to F. So since every NIC card requires a MAC address, that means that all of our routers and switches also requires MAC addresses on their ports. So I've gone ahead and I've put together just a double digit of letters for each interface. Now of course these are not valid MAC addresses, but I've done this to save space on the whiteboard. So we can see AA, BB, CC, DD, and so on throughout every single interface throughout the network. But of course, if you were to look at switch 3's MAC address on that interface, it would be the full 48 bits or 6 bytes. So what we need to understand at the CCENT level is to be able to look at a diagram similar to this and answer a few questions. So one of the questions that I think is really important to understand and to be able to answer is two that I've put down the bottom. The first one being, what is the IP or MAC addresses between router 1 and router 2? So what this means is as router 1 generates some data, creates its layer 4 and layer 3 and layer 2 header and sends it out onto the wire, as it traverses on a hop by hop basis, what would be in the IP header and Ethernet header as it traverses across this link between router 1 and router 2? So what would the IP addresses be? What would be the MAC addresses? What would be the TCP and UDP port numbers? And would anything have happened to the upper layer data? So maybe this was a HTTP GET message. Would the HTTP GET be inspected by router 1 or by router 2 at this point as it traverses across the network? If it is, then why would it be? And if it's not, why would it not be inspected by those devices? And then the second question that I've put together here is, what is the IP/MAC addresses between switch 2 and switch 3? So again, that's the PC has generated a data, attached all the relevant layer 4, layer 3, layer 2 headers, and then sent it out onto the wire. And as it's hopped all the way across into the 172.31.0.0 network, as it goes between this link, what do we expect the layer 2 or layer 3 headers to look like? What we also need to understand is not only is what is happening at the layer 3 and layer 2 headers and why, but are the routers or switches doing anything else? Now we learned previously that when a switch receives a frame in, it learns the source MAC address and then floods it or forwards it out the correct interface to the destination depending on the actual destination MAC address. And then when a router gets it, it goes through the decapsulation and encapsulation process on a per hop basis, and it also decrements key items like what we call the TTL, the time to live value, which is a attribute of the layer 3 header. Why is the TTL value decremented? So these are the sort of things that we're going to talk about on this video and be able to answer these two questions, why they are the answers and why they're not the answers. And what I mean by that is, like I said, as the packet between 1 and 2, what is and isn't looked at as far as these routers are concerned and why. Understanding the why and the why nots is almost as important as actually having the answer itself, because if you know what's not happening, then it's easier to troubleshoot more complex faults as you move forward in your networking career. Let's start by having a discussion around what's happening as PC1 generates the traffic trying to send it towards PC2. Once we understand what happens in detail, we can go back to the questions and hopefully we can answer them. So first of all, PC1 decides to do what we call a HTTP GET message. So this is PC1 trying to get a particular web page from PC2. Let's pretend PC2 has a local web service running on it. And what we're trying to do here is download a HTML web page. Now I don't care why. In fact, most network engineers don't care what the end user is doing. Long as the end user can get from A to B, we're happy. The only time we get concerned about what our end users are doing is if we have other jobs, like we're doing some sort of content filtering, or if we need to apply some sort of quality of service. But at this time, we don't really care about PC1 or PC2. All we want to make sure is PC1 can communicate with PC2. So PC1 goes to generate a HTTP GET message. Because of this, we know that the layer 7 protocol will be HTTP. And HTTP will work with the presentation and session layer. And this will become what we know as our upper layers. This gets passed down to our lower layers, where TCP will be invoked because HTTP runs on TCP port 80, and the IP protocol will be used at layer 3 with the destination as PC2 and the source of PC1. It then builds the layer 2 header, and we know from the previous videos that this will be Ethernet, and because it's Ethernet, it's referred to as a broadcast media access. It needs to do some sort of broadcasting or learning because there could be more than one segment connected to this switch. And in order to find the Ethernet details, we know the initial packet would use something called ARP, the Address Resolution Protocol. It will use ARP because the destination IP of 172.31.0.10 is not in the network that PC1 is on. And because of that, PC1 will have to send the traffic to its default gateway, which will be the .1 IP address of router 1 in the 192.168.0.0/24 network. So as such, an ARP is sent out onto the wire in order to obtain the MAC address of router 1. So the destination MAC address will be router 1, which in this case will be CC, and the source will be PC1, and that will get sent out on to the wire. And we know that from layer 4, which is from TCP, all the way down to here would be considered our lower layers. That's how PC1 creates the data for HTTP GET towards PC2. Now, what is very interesting to begin with is notice that the IP address is of the destination. Now that sounds a bit obvious right now, but keep that in mind because the Ethernet header is not the MAC address of the destination. Because remember, the MAC address and broadcast traffic and ARP and all of this can only be done within a segment. It can't be sent off a segment because routers stop broadcast. So an ARP message will never broadcast off the local segment. So because of that, we have to send it to our default gateway. So we know that the traffic will go up to the default gateway. In this case, that will be up towards router 1. Now router 1 will receive that packet inbound and will look at the layers 1 and up. Because remember, it receives it from the electrical signals and the electrical voltages, which is at layer 1. The next up from layer 1 will be layer 2, which is the Ethernet header. It will look at the Ethernet header and notice that the destination MAC address is for itself. It's CC. Now, because of that, it will decapsulate, as in it will take away the layer 2 header, and it will look inside and look at the layer 3 header. So it's removed its layer 2 header, and it's noticed that the layer 3 header IP is not for itself, and in fact it's for PC2. So router 1 at this point will do a few things. First of all, the TTL value, the time to live value, which is an attribute of the layer 3 packet, will get decremented. And the TTL value will get decremented by every layer 3 device in the path, so router 1, router 2, router 3, as it traverses to the final destination. Now switch 2 and switch 3 will not decrement the TTL value because these are layer 2 devices and the TTL value is part of layer 3. Now, because we have this TTL value that's able to get decremented, it allows us to track how many hops a particular packet has actually gone through. And the reason for that is because if router 1 decremented it, pass it to 2, and 2 decrements it, but for whatever reason 2 has a path back to 1, and it would create a loop in the network which may cause problems. When the TTL reaches 0, the device which decrements it to 0 will actually discard the packet. This is why the TTL is vital as part of the routing process. If there was no such thing as a TTL, a loop will occur and the network could actually fail. And this is why we need the spanning tree protocol at layer 2, because in the Ethernet header there is no TTL. So we know that TTL is going to get decremented on a per hop basis. What we also need to do, as the router receives its traffic in, is look at its routing table. Because we look at our routing table to look at all the entries of how to get to certain locations. And in this case, router 3 would have advertised to 2 via RIP or another interior gateway protocol how to reach the destination of 172.31.0.0, and router 2 would have advertised it to router 1. Because of that, router 1 knows to send it towards router 2 as its next hop. So router 1 now knows how to get to router 2, but what router 1 doesn't know at this stage is the layer 2 header to create. So as the packet comes in, router 1 will decrement the TTL. It will switch it to the correct interface because we know what interface to go out on because of the routing table. And then if needed, it will also perform an ARP to find the MAC address of router 2. And then from that, it will be able to create the layer 2 header and a new CRC, which is the cyclic redundancy check, which sits inside the frame check sequence. But normally the CRC and FCS is referred to as one of the same. And this is the check that goes on the Ethernet trailer. And this check allows router 2, when it receives the packet from router 1, to ensure that nothing, no voltages or interference has caused the frame to be corrupt across the wire. And if it has been corrupt, it will simply drop that frame. And that CRC or FCS is created on a per hop basis by a layer 3 device. So again, by router 1, router 2, router 3. Any traffic that PC2 sends and any traffic that PC1 sends. So as it was received in, it also would have had a CRC that would have been taken off by router 1. Now at this point, router 1 would have to create that layer 2 Ethernet header, but notice it will not touch the layer 3 header, and in turn, because of that, will not touch any header above it, because the layer 3 IP is for PC2, it's not for router 1. So router 1 will create the new header, and this new header will actually have the destination of router 2, which is EE, and it will also put the source as itself, which would be router 1 DD. It will be received inbound by router 2. Router 2 again decapsulating from layer 1 upwards towards layer 2, towards layer 3. It would first stop at layer 2 because the destination is for the interface of EE. Router 2 will look at the IP header and notice that the IP destination is not for router 2. Because of that, it will push it to the routing table and decrement the TTL value. It will look in its routing table to determine which interface to send it outbound in order to reach the final destination. And hopefully there's a match in the routing table, and then it's switched to the interface of FF. Because now it knows where to send the information, it then looks to find out if it knows the next hop's MAC address. In this case, does it know the MAC address of router 3, which is GG? Thankfully it does, so it doesn't require any ARP processing. And again, the layer 2 header is now created, but with the new values. The new values being the destination of router 3, which is GG, and the source of router 2, which is FF. Again, remember, layer 3 upwards is not touched because no one is the IP destination at this point. The packet is received in by 3.3 on the GG interface, and it's decapsulated because the destination is the MAC address of GG. As it's decapsulated, it looks at the IP address and says, okay, that's not me, so I need to again look into my routing table. Now, in its routing table, it will see as directly connected the 172.30.00/24/24 network, and it will notice that that's reachable outside the interface of HH. So again, it will switch it to the correct interface, decrement the TTL value, and it will then look at its ARP cache and determine whether it has the MAC address of PC2. Because again, it has to recreate that layer 2 frame. And along with that, it creates the layer 2 trailer, the CRC, or the FCS, the frame check sequence. Hopefully it does, and it enters the MAC address of PC2 as the destination with the source of PC3, HH, and sends it out onto the wire. Now, something I skipped over on switch 1 is as the frame leaves and enters the switch 2, switch 3 interfaces, what does the switch do? Well, we've gone over layer 2 in a lot of detail already, and we didn't discuss any encapsulation or decapsulation or packet rewrite as it goes through the switch. All we discussed was the switching concept and switching learning and forwarding process. So going back to that information, we know when that frame is received inbound on switch 2, the switch will, rightly so, look at the Ethernet header. It will learn that the R3 MAC address HH is reachable out of its interface II. It will look at the destination. It will look at the destination of PC2, and it will determine whether it has that in its MAC address table. If it doesn't have it in its MAC address table, it will flood to all interfaces apart from the interface it was received on. And as such, it will actually be flooded out towards this interface, out JJ's interface, towards switch 3. Now notice that no packet rewrite is happening, no encapsulation, no decapsulation, because the switch is just learning and forwarding based on the layer 2 frame. It does not remove the layer 2 frame. Because of that, eventually it reaches the PC. The PC looks at the Ethernet header and sees that the destination is PC2, which is for itself. The source was PC3. And because again, the device has received it with its MAC address, it will begin to decapsulate the layer 2 header. Once decapsulated, the PC will look at the layer 3 header and notice that the destination is for itself. So only then will the layer 3 header be decapsulated by the destination device. The destination device will then look at which process it's required. In this case, it was to TCP on port 80, so it sends it to the TCP process. TCP knows that because we're using the well-known port of port 80, then it must be some sort of HTTP message. The HTTP protocol gets it at layer 7 and 6 and is able to handle the process. A few things to mention before we start going back in the opposite direction with the reverse traffic is don't get fooled or confused by what I've put here on the switches. I've put II, JJ, KK and LL. Now we know that every single NIC has a MAC address. But we also know from our previous lessons that we didn't really get into MAC addresses on the switch interfaces. And the reason for that is because the MAC addresses on the switch interfaces are rarely used. They're only used if the switch itself was to send some sort of layer 3 information, or if traffic was destined for those interfaces themselves. If traffic is switching through the switch, like it is here between router 3 to PC2, what happens is it looks at that MAC address or CAM table. And remember, that associates MAC addresses it learned with ports it learnt it on. So for example, we could say that this was port 2, port 3, port 2, port 4, and it would say in this MAC address table that PC2 of MAC address, this MAC address down here, is reachable out of port 3, and HH, which is router 3, is reachable out of port 2. So remember, as layer 2 frames come into the switch, the destination and source MAC address is looked at, but it's switched to the outgoing port. But as traffic goes to the switch, either to the actual MAC addresses on the interface, it's then only processed by the switch itself. I just wanted to highlight that because I know that putting the MAC addresses on the switch ports and not the port numbers may confuse some of you. And the reason I've done this is because we need to understand the encapsulation, decapsulation, and packet rewrite on a hop by hop basis, and how it differs as it goes through a router as opposed of going through switches. In the opposite direction, we're going to get something very similar, but this time it would be PC2 creating the traffic. So as such, the 7, 6, and 5, again, our upper layers, will be part of the HTTP response. It too will also use TCP. But what's very interesting here in TCP is previously we only gave it a single port number of port 80. Well, that was the destination port number. We didn't really specify the source port number of PC1. But if you remember from a previous video, the source port number will be something called a ephemeral port, which is a random port number generated within a particular range depending on the application. So in this case, what will happen though is because it's the return traffic, the source and destination ports will be flipped. So in this case, the source will actually be 80 and the destination port will be whatever ephemeral port PC1 generated on the initial request. Let's say that was 3322. For the IP layer 3, the IP will be the 192.168.0.100 as the destination. So the destination will be PC1 and the source will be PC2. The Ethernet header of the first initial frame that PC2 creates, which will be towards its default gateway, which will be router 3 in this instance, because again the destination of 192.168 is not on the network that I am on, therefore I must consult my default gateway. So the Ethernet header at layer 2 will be the source of PC2 and the destination of router 3, and then that will get sent out onto the wire, and the switch 3 and 2 will receive those frames in on a particular port, in this case the port which the MAC address LL is associated with. Let's say that's port 4. It will look at the source and destination. It will update that the MAC address of this is reachable out of this particular interface for switch 3, and it will look at the destination and send it upstream towards the correct device without any encapsulation or decapsulation on the switches. Router 3 will receive it, and notice that the destination of the MAC address is of itself, so it will have the responsibility of decapsulating and encapsulating the new frame as it's sent onwards towards router 2. When router 3 receives it and it takes off the frame, it obviously would check the CRC to make sure the frame's okay, look at its routing table to find out which interface to send it outbound on. It will decrement the TTL value to prevent any loops. It will create a new layer 2 frame. It may involve some sort of ARP process in order to find the MAC address of the next stop if it's not already in its local cache. And it will create a new CRC or frame check sequence on the trailer as it's sent outbound towards router 2. And then that will happen on a hop to router 1. Router 1 will perform the same as router 2, creating a new layer 2 header, but this time with the destination of the MAC address of PC1. Switch 1 will switch it, PC1 will receive it, and PC1 will decapsulate all the way up to the HTTP response on the upper layers and be able to process that response from the initial HTTP GET message. So going back to the questions that we had to initially answer. The first question was, what is the IP address between router 1 and router 2? Or the IP and MAC addresses. So we know from our discussion that the encapsulation and decapsulation only happens at layer 3 devices. Layer 2 devices only switch the packets. We also know that the Ethernet header is also changed on a per hop basis as it moves from network to network, or from broadcast domain to broadcast domain, or from network segment to network segment. So as such, we know that the MAC address between router 1 and router 2 will be different than the MAC address it was initially built with, but the IP address will be the same. The answer to the question would be the MAC addresses and IP addresses used between R1 and R2 will be DD, EE as the MACs, and PC1 and PC2 as the IPs. Our next question that we were asked was, what is the IP/MAC addresses between switch 2 and switch 3? Again, we know that the encapsulation and decapsulation only happens at layer 3 as it runs between networks. As such, here it's already inside a single network. So as it's moving between switch 2 and switch 3, the IP and MAC addresses will remain the same. We know that the initial IP would be the same IP, so the source will be PC1, the destination will be PC2, so there's our IPs, and the MAC addresses will be the router 3 MAC address of HH and the destination PC2 MAC address highlighted just down here. So that's the answer to those two questions. Hopefully this helps summarize what happens on a per hop basis and how it differs between a switch and a router. As I said, this may be something that we've covered in various videos throughout the series so far, but it's very important that you understand what's happening on a per hop basis to then start to be able to answer and raise questions around why it has to happen and what other things need to happen in the background for this to have some sort of end-to-end communication. So for example, we've talked about communication on a segment and how to get off a segment. This is primarily used by ARP. The PC will go towards the default gateway. What we haven't spoke about, how then does router 1 and router 2 communicate through an IGP like RIP or OSPF in order to exchange routes in order for router 1 to know how to reach the destination network. But understanding what happens on a per hop basis and how to get off the local network is the first steps on building the bigger picture towards understanding the full end-to-end communication required. Okay, so that's all we've got time for in this lesson. It was a whiteboard session to discuss the encapsulation and decapsulation, sometimes referred to as packet rewrite, on what happens on a per hop basis as traffic travels through the network. We also had a discussion in the differences between how that differs from layer 2 to layer 3, where we said layer 2 switch the Ethernet header, where layer 3 actually performs the decap and encap as it processes it from one interface to another interface, along with decrementing that TTL value, and it knows which interface to switch the traffic towards based on the routing table, and it creates that new CRC or FCS on a per hop basis. I hope this video has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.